So now we're going to dive into trying to prove the inverse function theorem. I'm not going to present this as everything's laid out and as elegant as possible because I want it to be more realistic in terms of what would you do if you were trying to prove this. And a good way to do that is to actually just try to dive into a calculation instead of focusing on some of the theoretical aspects. And one of the things we want to prove is, we've got f going from, now we are going to go from Rn to Rn. That had better be true, or else it's not going to have an invertible derivative, which is the assumption. And we have some neighborhood v, perhaps. We'd like to know that there's some neighborhood v that maps 1 to 1 and onto f of v, so it's locally invertible, locally 1 to 1. And then you get an inverse function g just defined there, and we'd like to know that's differentiable. And the thing about that is that's a calculation, that's a limit. There's some manipulation we can get our hands dirty with, and then we'll probably get stuck, but then we'll see what we need to either assume or prove or work on when we get stuck. So we've got this situation. So g is the inverse to f. Let me actually give you one more picture that I'll keep referring to. We've got x, and then its image y. Here's our translation table, y equals f of x. And then we're going to be comparing 2 points because we're really looking at the derivative of g that we want to analyze. We're going to look at y, and then we're going to move that by some vector k, and so this is going to be y plus k. Okay. All right, so I guess I need a name for the image of that over here, because really we want to think of these as being able to translate back and forth, because on this local level, we're going to assume that f really is invertible to get the calculation going, and then see what's true about its inverse. And so this is going to be, let's say the difference between these two things is h, and this is x plus h. Okay, so really what we're defining is that h is g of y plus k minus g of y. And here's g of y plus k, here's g of y, because f of x equals y, and f of x plus h is y plus k. So it's just that these two pictures translate back and forth to each other. Okay, so that's going to set us up, I'll keep coming back to that picture, for the limit calculation. Oh yeah, one more notational thing. So let's let a denote the derivative of f at x. Okay, what should be the derivative of g at y, where y is f of x? Okay, well, this is something that comes out of the chain rule. The claim is this is just the inverse of df of x, df at x inverse. And that's because when you compose f and g, that's supposed to be identity map. And so the derivative of this composed with the derivative of this should be the identity matrix. That's the chain rule. Okay, so we actually know what to put in our limit calculation, and that's awfully helpful. If you're trying to prove something works, having it be more specific and more of a calculation and manipulation, that's always helpful. So here's the calculation we're trying to do. We're trying to take the calculation as k goes to 0 of, g, we're really analyzing g, because we know we're going to assume g, f is nice, certainly. G of y plus k minus g of y, and then minus a inverse k over the magnitude of k. We'd like to show that that is 0. That's the definition of saying the derivative of g at y is this matrix A inverse. And that's the calculation we'd like to do. Okay, so let's review just real quick what we have to assume so far. I've already assumed that f is locally 1 to 1 right near x, so that this setup makes any sense at all. Okay, so we're definitely going to have to go back and prove that. All right. There's another subtler thing that we just assumed here, which is when we do this limit k goes to 0, to make this really work out as the derivative, this is supposed to come in from all directions. It's not supposed to be just some limit k goes to 0 in only some directions. So that's not going to make any sense unless g is defined in a neighborhood of y. So not only does f have to be locally 1 to 1, it also at least has to the image of f of this open set V does have to include some open neighborhood of y. So in other words, we're basically saying, oh yeah, we better prove that f is an open map as well. Okay, those are going to be two separate issues, but they are definitely on our to-do list. Let's assume that that can be done, and it turns out that we're going to get some hints as to how to do that by actually proceeding with this calculation anyway. It's a great thing about doing math, really doing math, as opposed to the way books usually present it, is you sometimes go ahead with things even though you know there's missing pieces, and you just go until you get stuck and then try to get unstuck. Okay, so there's our calculation we want to do. Okay, let me see if I can avoid having to rewrite that. Okay, so let's just see what we can do. Well, we want to compare this. We want to get this in terms of the similar limit in terms of f and x and h and A, the matrix A. Okay, well, how do we get the matrix A inverse out of here and get a matrix A to come in? Multiply the whole thing by the matrix A. And what's the good thing about that? We're assuming that A is invertible. Oops, like you can't see that. Otherwise, we wouldn't even be talking about A inverse. Okay, so here's a limit of a sequence of vectors in Rn. If we were to show that that limit is 0, it's sufficient. It's going to be enough to show that A times that limit of vectors. I'll try and keep my G's and my Y's straight. It's a little tricky with this Sharpie. We're going to take that limit, we're going to multiply by A. We'd like to show that's equal to 0. Okay. Alrighty, but this, we can start working on that. This is something we can do. Okay, so that's A applied to g of y plus k minus g of y. A is linear, so that's going to give us at least something to do. And then, of course, A times A inverse, that's part of the payoff here, is that A inverse has gone away. And this scalar on the bottom just comes along for the ride. Okay, that's cool. Let's see if I can organize this a little. Alrighty, so let's go ahead and distribute in that A by linearity. Okay, that's A times the vector g of y plus k minus A times g of y minus k. Okay, now I'm going to start using my translation picture. Okay, remember that y was equal to f of x. H was defined to be g of y plus k minus g of y, but the main thing is that everything in this picture corresponds to the stuff in this picture. Okay, so let me see if I can have both of these things showing at the same time. I'm not using my usual whiteboard technique here, so it's a little tricky. Okay, that works. Alrighty, so this limit calculation. Alrighty, so this g of y plus k, that goes back to x plus h. And then it's A times that. Okay, minus, okay, g of y is nothing more than the original point, x, so that's ax. And then minus, now k was the difference between these guys, okay, that is y plus k is just f of x plus h, minus y is just f of x. Okay, so this can make your eyes glaze over if you look at it algebraically. If you just look at the picture and you just say, look, we're assuming that f and g are inverse functions here. We're not assuming anything else nice about f and g right now so much. But we're assuming that this picture corresponds to this picture. He's just really looking up in the dictionary, how do you translate all this stuff to x's and h's? That's all it is. Okay, now what happens? Ooh, look, the ax's cancel out. And this starts to look really familiar. F of x plus h minus f of x, ah. It's exactly the numerator of the calculation that would show what would be involved in looking at the derivative of f. Okay, so let's actually write that out. There's a minus sign, but that's okay, because we just want to show that this is 0 anyway. Okay, so this guy is going to be the limit as k goes to 0. So a minus sign in front. So I factored out the minus sign. F of x plus h minus f of x, and then minus, because I factored out the minus sign, ah, all over magnitude of k. Okay, so this is cool. Alrighty, this is pretty similar to the thing we know is 0, because the thing we know is 0 is the limit of this guy. If this were an h and this is the limit as h goes to 0, this would be exactly the quantity that must go to 0 for a to be the derivative of f, which is the assumption. Okay, so what I'm going to do is I'm going to fudge that a little bit. Obviously, that's a problem we have to deal with. That's a problem we have to deal with. One of them is a very easy and standard algebraic fudge. Let's just change that to h, but then multiply it by magnitude h over magnitude k. Okay, so this guy is going to 0. And hopefully we can deal with this. There's nothing complicated here. Sometimes it's a bad thing because there's nothing to manipulate, but it's actually going to be very interesting to look at this and see what do we need to know about f or g for this to work. And then there's this issue of the limit as k going to 0. It's not a limit as h is going to 0, but we'll be able to deal with that. Okay, so here's a list of 4 issues. Okay, the first one I just want to reprise real quick is that we need that the limit as k goes to 0, we need it to make sense. And that's really one of the number of reasons why we want f open. It's not the biggest huge reason, but it's one reason why that's on our to-do list. Okay, that's actually going to be the last thing to show though, because it's the most subtle. Okay, there's a very finicky issue, which is that by definition, we're taking this limit as k goes to 0. We're dividing by the magnitude of k. Oops, pointed too high, right? That doesn't make any sense if we actually allow k equals 0. And of course, one of the standard things about taking limits is you don't actually plug in the value. Okay, but if we're going to change this to a limit as h goes to 0, we better make sure that we don't accidentally end up having h equal to 0. But what does this say? Okay, this is a consequence, because remember, what is the translation? The h is the difference between these guys. The k is the difference between these guys. So we're saying that if y and y plus k are not the same, then x and x plus h had better not be the same. Okay. Well, that's just saying g is 1 to 1. But wait, where did g come from? We're assuming that g came as the inverse of f. So g is certainly invertible. It has f as its inverse, so it's certainly 1 to 1. Okay, so that's actually not a big issue. Okay, this is okay since g is 1 to 1. Now, of course, there's this other thing on the to-do list. How can I even assume that f has an inverse of any type whatsoever, even locally? That's the locally 1 to 1 issue, which we're going to have to come back to. Turns out we're going to get a huge hint in just a minute as to why that's going to, or how to do that. Okay. Okay, so now, a little less silly than the last one, we need to know as k goes to 0, h goes to 0. If we're going to translate this into being a limit as h goes to 0 so that we can recognize this as the definition of the derivative, okay, but that's exactly something that's going to be about g being continuous. Okay, because remember, h here was defined in terms of g. Okay, and so as k goes to 0, the inputs are shrinking to be the same. That's going to mean the outputs are going to be more and more the same, and so h, the difference, is going to go to 0 if g is continuous. Okay, well, obviously at some point we're going to end up wanting to prove that g is a continuous inverse, not just any kind of inverse, because we actually want to claim it's differentiable. Okay, turns out that's going to be implied by the next thing. It's really this guy. Well, for all these kind of subtle issues about limits and everything, it's really this guy that's going to be the key and a huge hint to the rest of the proof. We need this magnitude h over magnitude k to be bounded. If this is bounded, and this is going to 0, okay, so now we're going to say, okay, we can really replace that with an h because of this, as long as we can prove g is continuous. We don't have to worry about the whole denominator blowing up. The limit is going to make sense as long as f is open. Got a lot of laundry list of things to do, but as long as this guy is going to 0, then the only thing is that had better not blow up, because then that would cancel out this going to 0, or could likely cancel it out. As long as this is bounded, then we're good. Okay. Okay, wait a minute though. That's something we don't necessarily know. Let's write that out. What does that say? And I'll just write it out, and then that'll motivate the next video. Magnitude of h over magnitude of k. Okay. Remember, k was the difference between those two things on the right-hand side of the picture. I'll show it to you one more time in a second, so I finish writing. And then h was the difference between their outputs. And we get the size of that over the size of that. Okay, so where's our magic picture? right? Here's our picture. I'm losing my screen here. Okay, I think we're good. So we want to know that not only as these two get close together, as k shrinks, that these shrink together, we want to have some better control over that. We want to actually know that the ratio of the distances is bounded. Okay, well, we need this to be bounded. That has a name. That's called a Lipschitz condition. And I'll say more about that in the next video. But in one dimension, it's just that, like if I have a graph of the graph of g here, this is just the absolute value of the secant slope. The difference in the output values divided by the difference of the inputs. And so what it means is the secant slopes are bounded. Obviously, in multiple dimensions, it's not quite accurate to think about that. But for our purposes, it doesn't go far wrong if you just think of the one-dimensional intuition. Bounded secant slopes. That's what a Lipschitz function is. So an example of something that isn't Lipschitz is like the square root function. That's a continuous function, but it's not Lipschitz because the slope is unbounded when you go towards 0. Okay, so this is key. This is the first hint of the careful kind of geometric analysis we're going to have to do to prove this theorem. And versions of the Lipschitz condition come in all through. So we're going to take another theory development break in the next video to develop a couple of four variations, minor variations on the Lipschitz idea. And it'll turn out that that's going to be a big thing for the rest of the theorem.